right. Little Schemer Chapter 8. I should make a new file. Okay. Lambda the ultimate. Let's see what this is about. I'm guessing it's going to involve lambda. All right. Yeah, we should hide half the. Remember when we did remember and insert L at the end of Chapter 5? Yes, I do. Oh, remember what we did? Remember. We replaced EQ with equal, right? Because equal handles numbers and their version of EQ doesn't. You get an error if you try to use EQ. The built-in version that comes with Racket works with numbers fine, but I'm loading a file I got off the internet that has a custom stuff for Little Schemer that is overwriting the default stuff, and their version of EQ doesn't work. Can you write a function, remember F, that will use either EQ or equal? All right, so let's see what we did for remember. So you see we have null, the list is null, then we return the empty list if the first element of the list is equal to the first argument. Then we return the rest of the list, which I guess skips over that value. And this is just remove one member. So we just return, there's no recursive call here, we just return the rest of the list. Otherwise, we cons the first element of the list onto a recursive call. So, and you see where equals getting used. I guess I'm not understanding what problem they're trying to solve with using, maybe I'm just misreading the question. Can you write a function, remember F, that would use either EQ or equal? Like, what's the F? Is that a function? I'm not sure. I'm feeling a little lost. I'm just going to read. Oh, no, because we have not yet told you how. Okay. See, and this is an example of like having a million questions in a chapter. Not a million, obviously. I'm exaggerating, but it reduces the cost of like just like I'm not sitting here struggling to figure out the answer. I'm just like, okay, let's see what they say. And they're like, no. So then I just move on. So that's a good example of this, how I find this sort of method more useful in some respects than, 10 questions at the end of the chapter and just those 10. Because like reading the answer is not like as costly. It's like I don't feel the need to preserve each question and try and figure it out myself. I'm just like, okay, I don't know what they're getting at, so let's just read on. Okay, so with that said, how can you make remember remove the first A from BCA? Doesn't it already? Oops. Yeah. Yeah, I think it does do that already. Misreading? Can you make remember remove the first A from BCA by passing A and BCA as arguments to remember? Okay, that was like more basic than I thought they were. Okay. Like that's true, I didn't realize that's what they were asking. That's interesting. Like, yes, to use a procedure to do a thing, we give it the arguments. I mean, it's good to think about those things explicitly sometimes. I notice I've had this weird, I don't know what to call it, like bad habit where, and I haven't had this before. It's like a new thing that's popped up when I've been doing these exercises where I will just skip the like conned or the else or both. So I'm just like thinking of what I want to happen. And now that I think about it, I think the issue is I just thought of this as I'm saying this. For simple things, I'm used to using if. Like I find it more intuitive to use if, and then for if it's like first argument and then second argument. So you don't say else, it's just implied. It's just there's like the consequent and the alternative. But if you use cond, then you have to write else. And I've been using cond because I've been trying to follow the style of this book, which I think is reasonable. Like, we'll try it this way, that's fine. But I haven't quite like automated using cond for certain things. Like cond is in my mind it's like the 3 or more alternatives programming structure. So switching it to 2 has been an imperfect process for me because I've noticed multiple times, like I just forget. Like mentally I want to use if, and so if I'm not using if, I just forget some of what I'm wanting to do, like, or what I need to do. So anyway, that was a bit of a tangent, but like it's interesting the degree of mental automation that happens that we don't even think of, and then you don't even realize it until something breaks is kind of interesting. Anyway, so how can you make remember remove the first C from BCA? Pass the arguments on? Passing C and BCA. Oh, is remember F going to be some sort of higher order procedure or something? Is that what we're building towards? Because you see there's like a pattern here. How do you make remember remove the first A from BCA? By passing A and BCA as arguments. How do you make remember remove the first C from BCA? By passing C and BCA as arguments. How do you make remember F use equal instead of EQ? By passing equal in as an argument to this higher order procedure, maybe? I don't know. It's a shot in the dark, but let's see. By passing equal is remember F. Okay. Cool. We're learning things. Very exciting. What is remember F test AL, where test is equal to superscript 1? I'm silly. Like I was parsing this as a footnote for some reason. I don't know why. That's funny. Okay. It's just because it's like weird to just see equal like that, I guess. Like I'm expecting something to come after or something. But that's fine. A is 5 and L is 6253. So I'm guessing remember F is going to be using the function that you pass in order to determine what member to remove from the function. So test is going to return true when it finds the 5 in 6253, and the operation of remember F is going to take away that 5, so that we're going to have 623, I think, is going to be, that's the value of that. So let's see. 623, okay. What is remember F test AL, where test is EQ, A is jelly, and L is jelly beans are good? So EQ can handle words. So this is just going to be beans are good? Yep. And what is remember F test A, where test is equal, A is popcorn, and L is lemonade, popcorn, and cake. So it's going to be lemonade and cake? Boom. Okay. Try to write remember F. A hilarious error where I forgot to put L for null to check it. So I was just checking whether the empty list was null. And I was like, why isn't this working? Okay. So this seems to work. So this is just substitution, right? Like we've got our function, our value, and our list. And for the function part, I called it tests. I've followed their thing. So I just, instead of EQ or equal, I just put test. So it's very similar. Okay. Let's see. So null, yeah. Test. And then you return the rest. Otherwise, cons. Yep, looks good. I mean, there's the long way of it. What about the short version? Yeah. Null. Test, yeah. How does remember F test A act where test is EQ? It acts like the previous version of, like the first version of remember. Yeah. Acts like remember. And what about remember f test al, where test is equal? Well, it acts like our changed version of remember that we made. Yeah. Now we have 4 functions that do almost the same thing. Yes. Remember with equal, remember with or I should say remember with the equal sign, with equal, and remember f. And remember f can behave like all the others. Let's generate all versions with remember f. Okay. What kind of values can functions return? Well, they can, I think what they're getting at, given the name of the chapter, is they can return all sorts of stuff, data, booleans, but also other functions. Listen, atoms. Okay. That's what I guess we've dealt with so far. What about functions themselves? Yes. But you probably did not know that yet. But I'm way ahead of you. Can you say what lambda AL is? Whatever that is, it would return, like that's what we've been doing the whole time. And I guess that's how they want to train you to think about it. Is like lambda returns a function that takes the arguments a and l. Lambda al is a function of 2 arguments a and l. Yep, I agree. Now what is lambda a, lambda x, eq, xa? Yeah, I find this a little confusing, but for some reason, but I guess it's like this would return a procedure of 1 argument, which, yeah, I don't know how to describe it well. It is a function that when passed an argument a returns the function lambda x eq xa, where a is just that argument. Right, okay. So the nested lambdas is throwing me for a loop, but this is important to get straight. So say for a we have hat, like the word hat. I'm picking words because it's EQ, so we want to use words. So like this is how you give, maybe I could make this a little clearer. Hopefully that's a little clearer. So this is how we would give this higher level, this lambda a, the argument hat. Then when we do this, what we get back is a procedure, but it's a procedure that takes an argument x and checks whether it's equal to hat. So then if we want to use that procedure, we could do this, and then we get true. Whereas if we do that, then we get false. Because you know, we're checking whether x is equal to hat in both cases. And either it is or it isn't. Okay, so this is called currying. It is not called, thank you, Haskell curry. Okay, I don't get these references. That's okay though. Using define, give the preceding function a name. That I can do. And you can see that the behavior is the same as when we were doing it all in the interactive window with no name. I called it super lambda. They called it EQC. It's probably more descriptive in a way. This is our choice. EQC, where K salad is going to be a function that checks whether a value is equal to salad. Function that takes an x as an argument and tests whether it is equal to salad. Yeah. I'll rename mine theirs. They're similar. Right, so you see we have EQ salad. And if we give it the argument salad, then it's true. And if we give it the argument ballad, then it's false. True, where y is tuna, false. Okay. Do we need to give a name to EQ salad? No, we don't need to give it a name. We may just as well ask EQC x, y, where x is salad and y is tuna. Okay. Oh. Okay. That took a little thinking, but figured it out. So, remember f as a function of 1 argument test that returns an argument like remember with equal replaced by test. So the argument that we want as the argument that we're going to provide to the function, we put it like the highest level. So that's lambda test. And then, so that means that we'll be providing the test argument to my remember function, and then it'll be spitting out the function that's in the body, but with the test function like substituted into that body. And so once you understand that, it was mostly straightforward, except I had to think about, okay, so what about the recursive call? And since we're providing test as the argument to my remember f, when we make the recursive call, we have to do that as well, again, to make sure that the procedure, operates correctly. And then it does seem to work, so I did my remember f equal, and then the first argument was the word I wanted to remove, and the second argument was the list. And the first argument wasn't a member of the second argument, so the entirety of the list was returned. And then for the second example, I did have a word that was in the list, and so the list returned with that member removed. So, okay. So I can see right away it looks like there's a difference. Oh, because they've ellipsed out the hard part. Not really hard, but the part that required a little figuring. So lambda test al con null quote, yeah, test, yeah. So l's cons car l, and then yeah, the recursive invocation was the only tricky thing. Describe in your own words the results of remember f test, where test it returns a function. Oh, it returns a function of two arguments that checks whether the first argument is an element within the second argument, and returns, which is a list, and returns that list with the first instance of the first argument removed if the first argument is a member of the list, and returns the entirety of the list if the first argument isn't a member of the list. It is a function that takes two arguments, a and l. It compares the elements of the list with a, and the first one that is EQ to a is removed. Yeah, I mean, that was a more efficient way of saying what I said, but give a name to the function returned by remember f test, where test is EQ. Fine, blah, blah. All right. So we could just define I did remember 2 as remember f with the argument EQ. And then you can just invoke remember 2 directly on arguments after you do that. And tuna salad, tuna salad is good, or be salad is good. Do we need to give the name remember EQ to the function remember f test? No. You could just do, this should be BC. Oops. Type of the function. Yeah, see? So you could just do that. Yeah, so they agree. Yes, I already did that earlier. Complete the line cons car else and remember f so that remember f works. Right. You just give it the argument that it needs. That's all. What is remember FEQAL, where A is tuna, shrimp salad and tuna salad, shrimp salad and salad? What is remember FEQAL, where A is EQ, L is equal, EQ, equan. So I guess if we're just treating these as words, then it would be equal, equan, equalist, equal pair. Yep. Did you notice the difference between EQ and EQ? Remember that the former is the atom and the latter is the function, right? So yeah, they use italics for functions. That's their convention here. And now transform insert L to insert LF the same way you transform remember into remember F. Okay. So with remember, right, so let's maybe do the intermediate version first. So the idea here is I'm first making a version, or I made a version that takes all the arguments that we need. You see, we can tell it's working because, well, let me just do another one, right? So with the first one, I passed an equal as the test, and it replaced the 3 with a 0, or it inserted a 0 to the left of the 3, because that's what we want to do here. But then when I used EQ, it gave an error because it tried to use EQ on numbers, and EQ doesn't work on numbers. So you could tell that it's working. So, null, lat, we do the null test, empty list return, and then you do the test, first value of the lat and old, and if they're, in this case, if they're equal, we cons the new onto the lat, and that just gets returned, and otherwise we cons the first element of the lat onto a recursive call. Okay, so you get the idea. So, but that's just like an intermediate step. Now we want to take it up a notch. So with just a couple changes, like you notice, and this is good because I think there's a scheme problem I struggled with, a related issue. So it's good to go over this in a lot of detail. But so you see, for the intermediate version, I had all the arguments and then I passed all of them in recursively. I had all the arguments in one lambda. And with this version, I pull out the test into its own lambda at the highest level. And I've got the other arguments like a line below that. And then, so this is one change, is putting the test in a separate lambda. And then the other change is how we do the recursive call, where basically, over here, everything was in one grouping, whereas over here, because my insert L is just a function of one argument that returns a procedure of 3 arguments, as opposed to being what it was before, which is a function of 4 arguments, then we have my insert L grouped with its one argument, and then we group the procedure that's returned by that call, by that invocation, with the 3 arguments that we want to pass in recursively. All right, something on that. Okay, and then define, and then if we want, we can use that procedure, my insert LF, to define other procedures. Insert L equal, where we pass an equal, and then we can just, as the testing function, and then we just do my insert L equal directly on arguments, and it works. I'm just going to change mine from lat to L. So I just copy pasted that over. Yep. Well, hang on. Oh yeah, there was something about this earlier. So you can either cons new onto cons old onto CDRL, or you can just cons new onto L. So I think that's fine. It's just like a different style of doing it, depending on what you want to do. Gets you the same result. It is working correctly, right? Let me just double check that. Yeah, 1, 2, 3, 4, 5, and then we insert 0 to, yeah, no, that's right. Okay. Do it to insert R as well. Okay. Ooh. Right. Okay. So very similar procedure. And I think it was valuable to go over this one more time. So yeah, the lambda that's the function of the test values at the top. The rest of the arguments are in a second lambda, and then it's basically the same as insert R from earlier. For null of a list, you return the empty list. If the test is true for a comparison of the first element of the list and old, then you cons old onto cons new onto CDR of the list. Footer of the list rather. And then otherwise you cons the first element of the list onto the value returned by invoking the procedure, my insert our function with the same function, and then passing in as arguments the new and old values and the natural recursion of the list. Pretty straightforward. Okay. Lambda test, lambda new old, lambda test, lambda new old L, con null, test car L old, cons new, Footer L. Yep. Yep, looks good. Or insert R and insert L similar. Yeah. Yeah, they're similar. They work basically the same way. Only the middle piece is a bit different, yeah. Can you write a function insert G that would insert either at the left or the right? Whoa. I think so. If you can, have a dessert suggestion. Get yourself some coffee cake and relax. I haven't had coffee cake in a long time. That's not a bad idea. We actually make coffee cake. Very straightforward, actually. I don't know if it's worth it. There's certain desserts that are better made and certain that are better bought, and coffee cake seems like it might be a better one to buy. Okay. So, you ask which pieces differ. We'll get them both on screen at the same time. So, number of arguments is the same, null let is the same, the test is the same, the recursive invocation is the same. So, only the value returned when the test is true is different. That's the only difference between the two functions. Okay. So I think based on this, if this is working correctly, we should get 1, 2, 0, 3, 4, 5. Ooh, oh, I'm using numbers. I didn't take the recursion here. Okay, there we go. A few typos and parentheses issues. So 1, 2, 0, 3, 4, 5. Because I've passed in L as the insert pointer thing. Now, if I pass in R, it should do 1, 2, 3, 0, 4, 5. Yep. So, basically, if you give it L, it inserts to the left, and if you give it anything else, it inserts to the right. Now, probably a more reasonable way would be like, you might have like an error message or something, like check for L, do it one way, check for R, do it another way, and then, ask the user what the hell they're doing, but I'm just going to leave it like this. Because, you get the idea. It does the job. It wasn't letting me copy. Okay, there we go. Okay. So I think they're going to do this differently. They're talking about passing in a function that expresses the appropriate consing. See, I was basically setting like a flag or something. Like, here's the argument for the where to insert the new value. But I think they're going to solve this differently. So if we want to directly pass in a function, so what I did, I basically made a couple of functions, insert left and insert right. And then this is just a slightly different way of doing it. But then I made the arguments for my insert G, new old list for L, and F or function. And then for the F value, I provided insert left or insert right, and you could see if we do left, then the new value is inserted to the left of the old function or the old value. And if we do insert right, it's inserted to the right. So you see with the initial version of insert G, I sort of set a flag of where to insert the new value, and with the subsequent version, I made some procedures, some helper procedures, and just pass those in directly. So there's somewhat of a difference there. And I think they may have done it an even different way. Oh no, they have a slightly different, it looks like they did it this way. So SQL, yeah, cons new, cons old. Okay, I did cdr L. They're just doing L, so I guess they'll pass in the cdr. Yeah, so you see with their seq procedures, it's basically, you could do it exactly the same as I do it, or as I did it, except you just pass in cdr L instead of L directly. No, equal new old cdr L, else cons car L, recursive call. Oh yeah, so they wind up writing it as an argument of one function, which is fine. You can do that too. No objection. Now define insert L with insert G. All right, so a couple of typos and cleanup. But the other thing was, I actually initially put a lambda here, but like the lambdas, we're already returning a function. We don't need any more lambdas. Like this is, to be really precise, this is invoking a function that returns a function. So we don't need any more lambdas, we just need arguments. And so you can see we can now just give it arguments directly, and it's fine. Yeah, it looks pretty good. Okay, I have to remember to always test Descript, even if I just take a break and come back later for more in a session, because when I was initially trying to record stuff, I took a break and then I came back and I was going to start another video, but then I figured, well, let me just test again to make sure. And the audio wasn't working and I had to restart Descript for it to work. So, okie dokie. Right, so now they want us to do insert R. They want us to use their insert G to make insert R. That's going to be pretty straightforward. Insert L, that's why. Okay, so yeah. Well, now we have the comparison. Yeah, with insert L, we insert the 0 to the left of 3, and with my new insert R, we insert the 0 to the right of 3. So that's working. Yeah, pretty straightforward stuff. Is there something unusual about these two definitions? Well, I just saw that they said yes, but I didn't see the reason. Oh, let me copy paste that. Okay. Well, in terms of the stuff that we've been doing so far in the book, mostly we've had lambdas, but such that I even initially, as I think I mentioned earlier, tried to put a lambda in one of these definitions, but since they return a function that takes arguments, since for whatever argument we give their insert G or insert G, as we've defined it, we return a function that takes arguments, then we don't need a lambda. I guess the other thing is, well, I mean, we've used non-primitives to define procedures. But yeah, just that whole procedure, that whole method of using a function, creating function in order to define arbitrary functions in terms of that function is like a new thing. So this is more like the big picture thing, and this is sort of like the more mundane point that's related to the big picture concept thing. Okay, it seems like they might have a slightly different point in mind. Let's see. Earlier we would probably have written define insert L, insert G sequence, where sequence is sequence L, and define insert R, insert G, but using where is unnecessary when you pass functions as arguments. Oh, are they just talking about like how they would write or describe it? Because yeah, they generally do that thing where it's like, if one of the arguments is the formal parameter for it is A, in the specific example it's potato, they'll say like what's the value returned for this argument, for this procedure when for argument A, where A is potato. Okay. Is it necessary to give names to SQL and SQR? No, you could just call insert G with a CQL and then pass arguments to that. Not really. We could have passed their definitions instead. Okay. Define insert L again with insert G. Do not pass in SQL this time. Yeah, so we can just do the lambda directly. Yeah. Okay. So give it a slightly different name. My newer insert G, L rather. And their insert G. But then other than that, lambda new old L, cons new, cons old L. Yeah, it's the same stuff basically. So we're asking if this version is better than this version. And I don't think it's I like this version better because it's cleaner, but I don't know if there's like an objectively better one. They say yes, because you do not need to remember as many names. You can remember func name, your mind, where func name is SEQL. Do you remember the definition of subst? So we've got that right here. Lambda new old lat cons, right? So if the list of atoms is empty, you return the empty list. Otherwise, you check. Well, this was done in the old style of organizing the programs, but this would normally just be another cond line instead of a nested. But anyways, you check whether the first element of the lat is equal to old, and if it is, you cons the new value onto the remainder of the lat, and otherwise you cons the first element onto the value returned by recursive call. So yeah, and here they did the shortened version. Does this look familiar? Yeah. Looks like insert L or insert R, just the answer of the second con line is different. Subst. I don't know how you're supposed to say that. So we can do that. And then we can make another procedure that uses, oops, that's not what I wanted to do. My subst. 12045. Yeah, okay. So then we can define a procedure in terms of insert G that uses the procedure that we just defined. And then we can invoke it on arguments and in this example, replace 3 with 0. Right. Same idea, lambda new old L, cons new L. And now define subset using insert G. I already did that. And what do you think YYY is? Let's see. Lambda, an argument in a list. Insert G, sequarem. Oh, it's going to remove. Wait. Why is the first thing false? That I don't understand. Sequarem sounds like it's going to remove the first copy of something. So would this be something that removes the first false value from like a series of booleans or something? I don't know. Surprise, it is our old friend Rember. Yeah, that's where I'm not getting the step through the evaluation where A is sausage and L is pizza with sausage and bacon. What role does F play? Okay, I'm not seeing this one. I'm having some difficulty here. All right, let's just see what actually happens. We'll do the experimental approach. Let's use their example too. Y, sausage, oops, sausage, pizza with sausage and bacon, which sounds pretty good. I must have done something. Okay, so this gives us some information. So Y gets sausage, pizza with sausage and bacon. Then sequarem, I don't know how useful it is actually. Okay, their insert G is just returning procedures. Okay, so Just try writing what I don't understand about this. That gives you a place to start, right? Okay, so some things I'm a bit confused about this. The first thing I'm confused about is what role SecRem is performing exactly. Stuff like sequence L seemed actually performed some operation, but SecRem just seems to return the list. But looking at it, SecRem just seems to return the list. What else? Although it's not just returning the list, in fact, it's taking arguments. Okay. So their insert G takes this SecRem procedure. I was just looking to make sure I wasn't missing some ellipses or something. I'm like, this is the whole procedure, right? Okay. So, and then this returns a procedure, SecRem, which, okay, which has a function which returns. Okay, now I'm starting to understand a little bit. So SecRem is building on their insert G. And so it has like the SecRem version of their insert G, the function that's returned by invoking their insert G with SecRem as the argument function. In place of f, it has a function which returns the list that it's passed, which is the cutter of L. Okay, thinking about it more, right? And so we see SecRem returning the list. Okay, now I'm starting to get somewhere. Why is it returning and bacon? Because sausage is the value that this equal test returns true for. At that point, the list is sausage and bacon, so the cutter of the list is and bacon. Okay, almost there. So SecRem returns cutter of L when car of L is equal to the old value, which is the value that we want to get rid of, which in this case is sausage. That value gets returned, and then const has the previous values const onto it by the higher level recursive invocations. By the procedures at higher, by the invocations. Okay, I think that makes sense. Cool. Okay, so I think I understand the mystery function. So now we say what we have just seen is the power of abstraction. Very exciting. Abstract common patterns with a new function. Have we seen similar functions before? Yes, we have even seen functions with similar lines. Remember value from chapter 6? Having a performance issue. I'm going to try a different browser. So I think it was actually partially as my Backblaze backup software was running. It hasn't even loaded in Safari yet. Okay. So this was their value. Arithmetic expressions, and figured out what they were. And so by similarities, they mean the last three answers. I see. There's like a lot of duplication. Like equal operator NEXP, and then the value, and then yeah, so if the operator of the arithmetic expression is equal to and operator is defined as like the first, well, it depends on how we're defining arithmetic expression, but it's like the first or second element, the car or the car of the cutter. Then if that's equal to whatever value we're looking for, then we perform a certain operation. You know, they want us to write, can you write a function, atom to function, which takes one argument x and basically returns the appropriate function if the argument is equal to like the text value for that function. Because quote plus means that's like the, I was going to say the letter plus, but you know what I mean. It's not using the function, it's just representing the name of that function in text. Okay, so you can see, by the way, the multiplication symbol is a little different than the x, because I'm using x as a variable, so I figured I should actually use the multiplication symbol. Right, so we see it works. We see it pretty clearly, actually. Right. So we can see that when we input the value, given value, we get back a function that we would expect. And it even says, you know, often when it returns a procedure, it doesn't say much, but for these, it's actually saying it's a plus, it's multiplication, it's exponent. So that's cool. So let's see. Right. Yeah, it's pretty much the same. That would be, what is atom to function operator? Any XP is plus 5, 3. Yeah, and so you see the way to invoke atom to function on numbers is to pass it the operator and then pass the numbers to the procedure that results from the function that's produced by atom to function. So that's what atom to function does, is it takes an atom and it spits out a function that you can then pass arguments to. But with this way of trying to do it, you're basically giving plus 3, 4, right, I should say plus 3, 4 gets evaluated, it becomes 7, and then you're passing 7 to atom to function, and we use EQ question mark in atom to function, which can't handle numbers. So then we're trying to evaluate a number with a function that can't handle numbers, and so it's just a big mess. Wait. Okay, I'm not sure. But wait a second. Maybe I misread. So NEXP. Oh, I think I did misread. Right. Okay. Yeah. So scratch that. For some reason, I was just thinking of NEXP being passed in to atom to function. The operator actually takes the operator out from NEXP and returns it. So rather than NEXP being evaluated, we get operator operates on NEXP and returns, or I should say, how do I want to say this? The arithmetic expression NEXP, which in this case is plus 5 and 3, or the sum of 5 and 3, is passed as an argument to operator. Operator returns the atom plus, you know, the which represents the character for addition, but not the function addition. But then that character gets passed in, character's the word, as an argument to atom to function, which takes that character or that atom and returns a function. This is a good example, by the way, because this looks pretty simple, and yet I made a mistake, number one, and it was some effort to explain what was going on, number two, even though it's like, oh, this should be really straightforward, but, you know, sometimes not so much. Okay. Can you use atom to function to rewrite value with only 2 comm lines? Huh. Okay. So using the helper procedures as well that we made for value, I made a new value procedure. and I basically said if the n expression or if the arithmetic expression is an atom, we return the atom, or we return the arithmetic expression, which will be an atom. Otherwise, we invoke atom to function on the operator of the arithmetic expression, and well, yeah, no, I think that's right, yeah. And then we use that function that's returned by atom to function on the first and second sub-expressions of the arithmetic expression. I forgot the. Oh, and that's funny. I actually messed it up in the version on my blog as well, so I'll have to fix that. Yeah, because I forgot the recursive call. Because the elements of an arithmetic expression can be lists. Okay, so right. So this is the correct rewrite. Yeah. If atom is an arithmetic expression, or I'm sorry, if the arithmetic expression is an atom, you return that. Otherwise, you invoke atom to function on, or I should say, you invoke operator on the arithmetic expression, pass the result of that to atom to function, and then pass. Actually, I'm thinking about this. I'm not sure I fully understood how this worked before. But so we get the first sub-expression of the n expression, and then gets passed to value. And if that's like a nested arithmetic expression, then it gets evaluated recursively. I mean, it gets evaluated recursively no matter what. But if it's an atom, then it goes to the base case, and you just get the like if it's an atom, it's going to be like a number. So then you just get that back from value. Whereas if it's another arithmetic expression, then it has to break that down more. I'm kind of expecting a more interesting trace result. I guess just kind of spitting back the number. Yeah, and they point out it's quite a bit shorter than the previous version. Time for an apple. One a day keeps the doctor away. All right. So let me do a trace too. Okay, I thought I might have looped for a second because there were so many calls and the performance of the computer was so bad. I'm almost back to the buy Apple Silicon now camp. This is driving me nuts. It's so slow. It feels like it's going like one computation a second. I'm exaggerating, but it's palpably slow. It shouldn't be. I don't have that much running. I mean, the main thing is the screen recording, and Ulysses is just a writing program. I mean, I've got some stuff in the background running, but not to where with, quad core i7 and 64 gigabytes of RAM. It should feel like I'm running on, I don't know what the analogy would be. Anyway, right, so I again messed up the this is like a new pattern for me, this recursive invocation of a function that produces or that returns a function is not something I've done a lot of. I've used functions that return functions, but the recursive step. And so then what happens is I start wanting to pass all the arguments to the recursive call, and it's like, oh, that's not the right number. And then I try and fix that, and then it's like, oh, now your parentheses are screwed up. So, yeah. I also realized, by the way, I was doing the removal in Descript, where it removes filler words. And I don't know if it's my pattern of speech or what, but that seems to be causing some choppiness because I guess I very quickly transition from an to some meaningful content. But however the software tries to define the cutoff point between those, it doesn't do a very good job in my case. So I'm not going to worry about the stuff that I already did, but I'm going to just remove the silence and not remove the filler words from now on. So there will be more uhs, but I think it'll actually be more intelligible. So yeah, I never really fully trusted the filler word removal because it's a lot harder than detecting silence, you know? So it's a lot harder of a problem. Okay. So let's see if we got that right. Or actually, let me just paste my attempt here. My attempt. Let's see if they agree. Yeah, I used F question mark and they used test question mark. They said lat and I said L. You know, you say potato and I say potato. I don't think it matters too much. I'm kind of surprised they haven't introduced the abbreviation for quote yet. Because it's like 5 characters to 1 character. That's kind of a big deal, you know? Anyway. So, null L return the empty list. Test. They did the test in the different order, but that's basically the same. So if the function returns true, if the test function returns true for A and char of L or lat, then recursively call multi-rember F with the test function and then invoke the function that's returned from that on A and cdr of L or lat. That agrees. And then otherwise cons the first element of the list onto the value returned by first, invoking multi-rember F with test and then passing in as arguments to the function returned by that, A and cdr L or cdr lat. So I think this agrees in essence, or not. Their solution is essentially the same. Okay. What is multi-remember F test A lat, where test is EQ, A is tuna, and lat is shrimp salad, and tuna. So it'd be shrimp salad, and that's it. Wasn't that easy? Well, yes, actually. The way they built up to this, I'm not quite at like mastery yet because I'm still screwing up some. Like it's not totally autopiloted for me how to write these, but it's at least to the stage where it's quickly corrected. Like I'm like, oh, whoops, I did that thing again, and then I can fix it. So, yes. I mean, that might be a little presumptuous on the part of a book, though, because like somebody might be like, no, actually, that was pretty darn hard. So, I kind of don't like it when a book takes a position as to the how easy something was, because somebody might feel bad. They're like, oh, this is supposed to be easy, so I'm dumb because I didn't get it, which is really common. Does multi-remember EQ or define multi-remember EQ question mark using multi-rember F? Okay, I think I could do that. Q question mark lambda, or no, not lambda. It's another bad autopilot. Right, because y is we're gonna get a function back that takes arguments when we invoke multi-rember F. So multi-rember F, and oh no, we don't want to use for EQ. For EQ, we don't want to do numbers. I like using numbers in general because they're short and you could type, you know. I mean, I guess you could do individual letters too, but I don't know. I like numbers. But we don't want to use that for this one. So potato, tomato, cheese, pizza, potato, ice cream, potato chips, potato salad. Right? So it works. It's fully operational. We're rolling now. Oh, wait, what did I do? Wait, no. Wait a second. Oh, I'm confused. Multi-member EQ and then multi-member app test where test is EQ. So I'm just going to read on. Because I thought the point was to have something that would be like using multi-member to define a procedure that would use EQ that we could invoke directly. That's what I thought the purpose was. But maybe I misunderstood. So I think the way I did it is right, and they're just saying it in a different way for this part. And then they say, we really need to tell multi-member F about tuna. And their answer is, as multi-member F visits all the elements in lat, it always looks for tuna. But yeah, I mean, you have to say what, I mean, you're not really telling, you're telling the function returned by multi-member F about tuna. But yeah, you have to do that if you want to remove the word. Does test change as multi-member goes through lat? No. No, wait. Now I'm wondering. No, test stays the same. The only thing that changes is, like the list changes because you recurse through it, but the other values don't change. Now, test always stands for EQ just as A always stands for tuner. Okay. Can we combine A and test? I didn't see what they said. Can we combine A and test? Oh, sure. You could make a function that's like preset to look for a certain value and take an argument and see whether the argument matches that value. Right. Well, they say the same thing. Test could be a function of just one argument and could compare that argument to tuna. That's right. How would I do that? The new test takes one argument and compares it to tuna. Right. That's what I said. Here's one way to write this function. I'm just going to read it since they. Okay. Right. So we had the EQC procedure that takes an argument, which I made my EQC. It takes an argument. I might just start using their names for stuff, by the way, because it actually gets a little confusing. But anyway, so yeah, it takes an argument and then it returns a function that compares an argument to the argument that was previously taken and sees if they're equal. Right. So they used a function generating function to come up with the equal tuna function. The only other way I could think of it is you just code it directly, where you just put tuna in the function directly, and then you do that. And so they say, oh, so I think I misunderstood. They were asking, I was thinking of another way of accomplishing the purpose of the function. I think they just wanted like literally another way of representing the function that they already made. So that was a misunderstanding. Okay. Have you seen definitions that contain atoms? Yeah. Quote, yeah. Perhaps we should now write multi-member T, which is similar to multi-member F. Instead of taking test and returning a function, multi-member takes a function like EQ tuna and a lat and then does its work. So in this model, the function like EQ tuna has the argument that we're looking for and also the test. And so what we're giving multi-member T is the function and the lat. So since the function is already going to have the value that we're looking for, then we just need to give the function the first value of the lat so that it can complete its job. So when the, yeah, this is lagging so much. I'm going to try a different version of Racket. This is Unacceptable performance. You just keep trying stuff until you find something that works. See, Windows Server is also using up lots of CPU. This seems a little better for now. Anyway, so yeah, we just need to give function the first value of the lat. And then if that returns true, we want to, so let's remember, multi-remember isn't a function that returns a function, it's a function that returns a value. So I'm going to pass in the function again, and then the natural recursion of the lat, and then otherwise, oops, we cons the first element of the lat onto the recursive call to multi-remember T. Okay, save, and this is already being slow again. Ooh, it's brutal. All right, so that seems to work. All right, let's see. It's not really difficult. No lat, yeah. Test or F in my version. Carlat. Multi-remember T. Yup. Cons Carlat. Yup. Looks good. Their version is essentially the same. What is multi-remember T test lat, where test is EQ tuna and lat is shrimp salad, tuna salad, and tuna? It'd be shrimp salad, salad, and. It's easy, it's not bad. How about this? Remember and company. What's coal? I haven't done this without knowing what coal is, which has just been introduced. Now that looks really complicated. Yeah. Well, I mean, it doesn't look super. It looks like the pattern looks similar, but I mean, there's new lat. There's just some new stuff here that hasn't been introduced before. Here's something simpler. Okay. A friend, lambda xy null y. What is this doing? You give it 2 arguments and it checks whether the second one is null and returns the value. Yes, it is simpler. It is a function that takes 2 arguments and asks whether the second one is the empty list. It ignores the first argument. Okay. What is the value of multi-remember a lat coal, where a is tuna, lat is strawberries, tuna, and swordfish, and coal is a friend? Ooh. Oh. So for the first thing, it seems like it would just, so if the list of atoms was null, which it isn't, then we evaluate this, but the value returned is just going to be the second one, because the first one's going to get ignored, so it winds up being the same thing. Same thing meaning like just the empty list. Same thing as we've seen in a lot of other procedures. And then Carlat is equal to A. Well, let's look at the else first. So you get a recursive call to the procedure with A and the natural recursion of the list of atoms and this lambda expression. Okay. So I partially understand this, but I don't know what's going on with the lambda. They said this is not simple. Yeah, I was trying to figure it out, book. So let's try a friendlier example. Okay. What is the value of multi-member ALAT call where make this bigger? Get the procedure on there too. Where A is tuna, lat is the empty list, and call is a friend. So if the empty list, then null for lat, for this example, null for lat would return true. Oh, so coal would be a friend. So would you just return? See, I was thinking about returning the procedure, or I'm sorry, about returning the value, but that's a mistake because a friend checks. So a friend would ignore the first quote, check whether the second quote is empty, whether the second part of this expression is empty, the second argument to a friend. And then I guess since it would be empty, it would just return that. So it would return true. True because a friend is immediately used in the first answer on two empty lists, and a friend makes sure that its second argument is empty. Okay. So I managed to step through the really easy example at least. And what is multi-member? Now lat is tuna and Cole is a friend. So it wouldn't be null. So then we'd see whether carlat is equal to A. It is. So then we'd recursively call multi-member and co with cdrlat, which would be the empty list. Well, with the argument with tuna, with cdrlat, which would be the empty list, and with a procedure that takes two arguments, newlat and scene, and would then invoke a friend on the first argument, which would be newlat, and the second argument, which would be cons carlat scene, and then evaluate whether the second argument was empty. So newlat would just get ignored. And I'm not sure where a value for scene would come from, but carlat would be empty. Wait. Yeah, I'm still confused about this lambda. But I think the result would be you just get back an empty list for this invocation. So let's see. Multi-member asks equal carlat quote tuna, where lat is tuna. Then it recurs on the empty list. Okay. What are the other arguments? Yeah, this is where I'm getting stuck, I think. What are the other arguments that multi-member and co uses for the natural recursion? Well, it uses col, which is a friend, which is a function. The first one is clearly tuna. Yeah. The third one is a new function. The third argument is a new function. Okay. What is the name of the third argument? I think it's an unnamed function. It's a lambda. We haven't given it a name. Oh. Oh. Col. Yeah, I mean, yeah, okay. I mean, I see that that's the third argument to this function. I was just thinking of it like, what is the name of this thing, this new function? But yeah, okay. Do you know what col stands for? No, I do not. The name col is short for collector. A collector is sometimes called a continuation. Okay. Okay, I may have possibly solved the performance issues, but via the rather extreme measure of turning off each display having its own space in the Mac OS settings, which I actually had done before, and I had turned that on recently, but I'd had performance problems running some software before, I forget what, and I noticed that turning that off seemed to help a lot. Turned it back on recently because I was trying to watch some videos full screen, and you can't actually do that very well if each display does not have its own space. Then when you make a video full screen, the other displays like black out, which kind of sucks. So I guess I'll just have to do that until I get a new computer. Like, you gotta log out to change the settings, so it's not like something you can flip on and off very easily. Anyway, so but hopefully I'll be complaining less about the performance of my computer from here on out while trying to make these videos. Okay, so we're looking at the new collector. So they've got this collector function or definition, and they're asking us if we could write it differently. Just gonna see what they say. Do you mean the new way where we put tuna into the definition? Yeah, I'm not sure what where col is a friend. Yeah, I mean, you can hard code values into the what I was looking for. Okay. We also replace Cole with a friend in such definitions because Cole is to a friend what Carlat is to tuna. Sure. Yeah, you could just substitute it in yourself. New friend, a friend. Yeah, sure. So multi-remember and co finds out that no lat is true, which means that it uses a collector on two empty lists. Lambda a lat col on no lat. Okay, so I think I figured out what was confusing me. Sometimes if I just read, like I try and write something and I'm like, wait, that's not quite right. So what I was saying was, so we pass in, so we invoke this multi-remember and co, a lat col, a is tuna, lat is the list tuna, and col is a friend. And then I was saying, so initially, lat is false, that's okay. So we skip to the next line. Equal carlat a is true, so we recursively invoke multi-remember and co with tuna as a, that's true. The empty list, which is the current cdr of the list, as lat, that's true. And a friend as col. Now, that's not actually correct. A friend is what's passed in as col initially. But what happens is that a friend gets used by this lambda to create a new procedure within the function, which then becomes the new col or collector within the recursive call to the argument. And what does this argument do? The function that's returned by the lambda is a function of two arguments which invokes a friend. The first argument passed into a friend by this function is the cons of the car of the lat and the argument new lat. The second argument is the argument seen. And then continuing the analysis of the procedure, no lat is true within the recursive call. I'm starting to get somewhere with understanding this. So no lat is true within the recursive call, so we invoke our call procedure, the function of two arguments involving a friend that I was just describing above. We invoke that on two empty lists. And that's a good point, because if the list of atoms is empty and we try and call car of lat on them, and so you see cons car of lat, but if it's empty, how are we gonna? Oh, wait a second. I'm at the wrong one. I was thinking of what the lat is at the within the first recursive call, but the function is passed in to that recursive call from like a level, one level above in recursive steps. So this lambda function is going to cons not the car of the empty list, but the car of the list of the list that had tuna. This list, I think. A friend skips over the first argument, and then it looks to see is the second argument, which is the cons of car, tuna, and the empty list null, because that's how we defined a friend. And it returns false because it's not null. They say multi-remember finds out that null lat is true, which means it uses the collector on the two empty lists. Which collector is this? This is new friend, which, a friend, and then it's two arguments, and then cons, car, tuna. Okay. Yeah, I think I'm following again now. How does a friend differ from new friend? New friend uses a friend on the empty list and the value of cons quote tuna quote. Yeah, it's like new friend sort of at a higher level because it's using a friend. And what does the old collector do with such arguments? The answer is false, as we saw, because its second argument is tuna, which is not the empty list. Right, because it's checking whether the second argument is null. That's how it works. What is the value of multi-remember? Yada yada. where tuna, A is tuna, and lat is and tuna. Oh, and a friend again. So, and tuna is not null. Oh, I'm looking at the wrong thing. And tuna is not null. So we see whether equal is quote to, or equal is quote, whether the first element of the list, which is and, is equal to tuna. It's not, so then we go to the else. We invoke multi-remember co with tuna and with tuna the word and tuna the list and a procedure which conses, all right, it conses and onto, and I realize there's another sort of nuance. So if you return a function, you can return a function that takes arguments and do stuff, and then does stuff to those arguments, or not. And it's important to keep that in mind. Like, so this lambda is going to return a function of 2 arguments, and then pass those arguments in some way to other functions. And they're ultimately going to wind up being passed to a friend, which is going to be where Cole is. But one of those arguments, newlat, is passed in a modified form because it gets something const onto it. Whereas another of the arguments seen is actually just kind of passed in directly to a friend. But if you just think, oh, you're just passing in 2 arguments, and you don't think about what's happening to them, the intermediate stages, you can get a little lost like I did. Okay. So Antuna is not null, and carlat of that expression, which is and, isn't equal to tuna, so we go to the else clause. We pass in tuna as the new a, and we pass in the word tuna as a new a, and the list tuna as a new lat, respectively. As a new col, we pass in a procedure that conses and onto the first argument of the procedure, new lat, taken by the procedure, which is new lat. The result of this consing serves as the first argument to a friend. The second argument taken by the lambda procedure seen is passed to a friend directly. Within the first recursive call, lat is still not null. Tuna now. So we go to the EQ line. Carlat is equal to tuna. So we make another recursive call. The new call in this recursive call is a procedure. I think this is going to be an important step to figure out. Yeah, I think I've decided I actually need a tree to represent this because it's getting a little complicated. I actually again messed up the representation of what col is in the tree like I did in text initially. But because I said that col was a friend, but col is, or a friend is like, it's invoked within the procedure that's called, but it's not the procedure itself. All right, I'm still getting a bit lost on this, so I'm just going to read ahead a little bit. Right, so they say, what is the value of multi-member co a lat friend, where a is tuna and lat is and tuna? They say this time around, multi-member and co recurs with yet another friend. Right, and they have here what I've depicted over here. See a friend, cons, and new lat, and then what is the value of this recursive use of multi-member co? False, since, wait a second. They say for this value, the recursive use of multi-member and co is false, since a friend, list 1, list 2, where ls1 is and ls2 is tuna is false. Well, so see, this is I'm not sure I understand. Because I thought the Lambda procedure was getting passed in as the new call, but they seem to just be analyzing this as if this is the end of, this is where the analysis ends. I'm not sure I understand. Let's see what they say. What is multi-remember and co? It looks at every atom of the lat to see whether it is equal to A. Those atoms that are not are collected in one list L. The others for which the answer is true are collected in a second list, LS2. Finally, it determines the value of F LS1, LS2. It's a good thing I looked at their explanation, even though it was a bit summary. I think I'm starting to get it. So notice the structure. So we've got a function. Okay. So we've got a lambda of 2 arguments, and then we've got a function. And that's true in both the equal line and the else line. Now for one of them, I see, okay. Like sudden galaxy brain moment. Okay. So leaving the null to one side for a second. So if the first element of the list of atoms is equal to the value, then we recursively invoke multi-remember and co with, A and the natural recursion, and then this thing. And this thing, in that case, cons is the first element of the list onto scene and leaves new lat in place. So the way they want you to think of these are 2 lists. These arguments to the lambda are 2 lists. And if this returns true, then we cons the first element of the list onto the second of those 2 lists. And if this does not return true, and assuming the list isn't null, then we cons the first element of the list onto new lat. And that explains why new friend is consing quote tuna. Because I was trying to think of like the function is somehow getting changed. But when it's the just the arguments that are getting changed is currently. Oh, I was also thinking of the lambdas, I think, as somehow getting evaluated on the way down when they're not going to be able to get on the way down the recursive chain, when they're not going to be able to get evaluated, I think, until like you hit the base case and then you get the empty lists, and then the stuff starts percolating back up. So I think that was another misconception. Yeah, so a friend does get substituted in. I was overcomplicating what was going on because I misunderstood, and that's why I was getting lost. If we go down a step, a friend gets substituted in for call. We go down a step, a friend gets substituted in for call. There's not some sort of like weird morphing procedure like I was imagining. Actually, it might. The procedure does. I'm still a little confused. I'm gonna have to come back to this. All right, so I found a Stack Overflow question about this procedure that I'm trying to understand, which is pretty cool. So somebody says, explain the continuation example on page 137 of Scheme. Actually going to put this. Cool. Okay. So he pastes in the document, not the document, the code, and he says, I've been staring at this all day, but I can't seem to quite seem to understand it. When you recur on the function, you're redefining call, but in the examples, they seem to use the original definition. Yeah, this was the confusion I was having. Why wouldn't it change? How can you recur on it without passing in the parameters new lat and scene? it's hard to explain my question because I seem to be just missing a piece. And then he asked for a walkthrough. And yeah, I think I got a bit further than this guy, but I was still grappling with the same issue and like sort of two incompatible understandings of what's going on with the recursive calls involving the call and the lambda functions that I keep flipping back and forth between. So there's obviously, a problem there. So this friendly person says, for simplicity, I'm going to use list as a collector continuation, which will just return a list of arguments to the continuation. Okay. So we've got foo as the argument, foo bar as the list, and list as the function that we're passing in. So a foo, lat, foo bar, call list. Okay. At the first iteration, EQ car lat, car of lat, a condition matches. Since lat is not empty, then the first element of lat is foo. This sets up the next recursion to multi-remember encode thusly. So we've got the original invocation, these are the values, and then because the EQ condition is met, the first recursive call, second total call to multi-member encode winds up being foo for a, bar for lat, and this value, this function with list in place of the call. Right, so there's some lack of understanding or something that I've been having here. So the value that we pass in for call is substituted in, or the function that we pass in for as the collector is substituted in to the lambda that gets passed in the recursive call. And then, but that function that lambda returns is now the new call in the recursive call, in this case in the first recursive call. At the next iteration, the else matches. So the else matches because the lat still isn't null, but it's not equal, foo isn't equal to bar. Yeah. Thus for the next recursion, we then have, this is what I've been struggling with figuring out. So for the second recursion, so we've got lambda new lat scene, and then function previous call substituted in as the call here. So the function is changing. And then that function of two arguments from the previous, the higher level iteration, I think is going to be passed, like that function is going to be passed the arguments that we're providing for this iteration. So with a lot of recursive functions, you like, sort of you get to the base case and then you build something up from like the base case back up to the top. But with this, it seems a little different because like rather than the empty list being like the most nested thing, they're like, that's kind of like they're being passed in as arguments to the topmost lambda. So that seems kind of different, right? So with that structure or whatever you want to call it, new lat 1 and scene 1 become the empty lists, and cons and bar gets consed onto new lat 1 because when bar was the a value, that wasn't equal to foo, or I should say, when bar was the car of list of lat, that wasn't equal to foo, and so we went to else. we went to the else clause, and so we wound up consing bar onto new lat, right? So after we do those evaluations, then for the innermost lambda, we now have the arguments bar and the empty list foo onto the second of those. And so then we have list bar and foo. Okay. I'm going to need to reread this one and read this further explanation. That's so I think I'm getting somewhere with it, but man, there was like a massive like difficulty spike on this book that was kind of sudden. Anyways. All right. So from the Stack Overflow thread I was looking at, I found this blog post. And the beginning sounds pretty promising. It starts off, the purpose of the little schemer its authors profess is to teach you to think recursively and to do so without presenting too much math or too many computer science concepts. The book is a ball to read. However, from the perspective of this reader, who is fairly new to functional programming and totally new to Scheme, the book gets almost asymptotically more difficult and complicated towards the end of Chapter 8 when we hit the function multi-remember and co. Yep, I agree, and I noted that there's a big jump up, which, you know, I don't think that was intentional. I think it was a mistake of the authors, but, you know, I mean, it's hard to make custom or mass market learning tools. But yeah, like it seems like a lot of it seems like maybe that they could have caught this one, like a lot of people get hung up on it. So especially given the goals of the book where they're trying to do like tiny steps, it kind of sucks if there's a big jump in difficulty. Looking around on the web, I noticed quite a few people had also hit this speed bump and were scratching their heads on how to go on. I think I can offer some assistance. So as threatened yesterday, I now unveil my initial contribution to the wild world of Lisp, my explication of multi-remember and co, and the concept of currying. Here's hoping I don't embarrass myself too much. Little Schemer is the latest iteration of the Little Lisper and is presented as a dialogue between teacher and student. Each chapter is a little more complicated than the previous, and questions get slightly harder as you go. It's like walking up a steeply graded hill until you get to page 137. Yeah. So he shows the function. Says the first clue to dealing with this function is context. The previous pages of TLS deal with currying, in which you define a function like lambda x, lambda y, and then equals xy. It takes one argument, parameter x, and then returns an inner function, which also takes one argument, parameter y. The value you pass is x to customize the inner function by binding the occurrence of variable x in the inner function to the value that you passed. So chapter 8 is about the practice of wrapping functions in this way. The chapter is also about passing functions as arguments. The first line of multi-remember and co lambda a lat col defines three parameters. The variables a and lat are by convention used for an atom and a list of atoms, but col is a function. You have to pass multi-remember and co a function that it uses inside its own definition. TLS admits that multi-remember and co is complicated. That looks really complicated, says the student. And it seeks to simplify the function by defining functions to stand in for A, the function that will be passed as col, and B, the first inner function defined in the con branch, EQ car lat A, and C, the inner function defined in the con else branch. To try to make you feel better about being up to your eyelids in deep water, the TLS authors give their functions friendly names like a friend and next friend. But I prefer names that tell me what role the functions play. So here are my renamed functions. TLS walks you through an execution of multi-remember, and so will I. To further simplify things and reduce the amount of typing I have to do, I'll change the example in the book. Instead of a forward lat, let's use berries, tuna, fish for our list. And you see he's renamed net lambda when match on net lambda when differ. When the function is called the first time, A is tuna, lat is berries, tuna, fish, and col is last function. This is a bit different than a friend. Just not worry about that. You can still follow the example. Carla is berries, which is not equal to tuna, so the else branch executes. Well, to remember, co is called with tuna as A, tuna, fish is lat. We pass CDR lat, and so we lose the berries, add them at the front of the list, and when differ as col. But wait, we're not just passing the when differ function we defined above. Here's the definition. This definition contains a variable lat that has a value at the time multi-remember and co is called recursively. Berries, tuna, fish, so carlat is quote berries. What we've got here is a version or an instance of when differ that has a value bound to one of its variables. Oh, this is like currying the binding of values to the variable of a function and then using this altered function to do something. I think that currying, however, refers to wrapping functions so that only one variable at a time is a given value. What this apparent creation of a specific instance of the function when differ does have in common with currying is this. Both use closures to encapsulate the instance of the function with bound variables, or to be precise, to make a copy of the function with its own scope that will persist so long as there are references to the closure. Any references in essay. There's something else in when differ that will bind to a value col. The function passed, remember, is last function, so we can and should substitute in that definition. So we're changing this to, we're substituting in this for quote berries, and we're also changing that. Let's give a unique name to the instance, technically the closure of the function when differ that has these two values bound to it. When differ 1. Let's write it out and set it aside for later use. So we see when differ 1. Well, I'm just going to keep writing for now, actually. Iteration 2, we're going through the lat. EQ, carlat A yields true. The other branch of the con executes. Well, to remember, co is called with tuna as A, fish as lat, and when match as col. Once again, thanks to currying, the definition of when match contains expressions which values are bound. Carlat becomes quote tuna, and col becomes when differ 1. Remember, we just recurred by calling multi-remember and co with when differ 1 as a function for the parameter col. So now let's define the resulting instance of when match as when match 1. And we see, the procedure, we're building up this like chain. When match 1 invokes when differ 1, invokes, last function. And it's like a custom chain of functions depending on the arguments that, like the functions are being customized depending on the arguments that we pass in, which is, that's part of what I found it a little hard to wrap my brain around. On to iteration 3, we're nearly there, which we can summarize like this. This time tuna and fish don't match, which means we're going to recur with another version of when differ 2, which invokes when match 1. And iteration 4, this time lat is an empty list, which means null lat is true. Terminating line, col quote quote is executed. Yay, we're done, except the result of the completed execution col quote list has to be evaluated. Here's everything where everything turns inside out or right side out if you like. First, the value of col in the final iteration was when differ 2. Right. When differ 2 was passed in as an argument to the final iteration, and then null was lat, so when differ 2 was passed in as col. So then when when the lat is null, when that condition is true, the function that's serving as call, as the collector, gets invoked on the two quotes. Or, I'm sorry, on the two empty lists. Now look back up and get the definition and substitute. All right, so when defer to was when match one. So when defer to is an argument, or a procedure, I should say, of two arguments. Right, so what was I saying? When defer to is an argument, I'm sorry, a procedure of two arguments, which invokes when match one, which is itself a procedure of two arguments, or a function of two arguments. And when defer to invokes when match one, the numbering these really and giving them names really does make it easier to talk about them. So when defer to takes two arguments, new lat and seen, and invokes when match one, which also takes two arguments. And the two arguments that when defer to passes to when match one are number one, the cons, or I should say fish as text const onto the first argument taken by when defer to, which is new lat, which in this case is the empty list. So cons of quote fish onto the empty list is the first argument that's passed to when match one, and the second argument is the second argument that when defer to takes, which is again the empty list. All right, I'm just like barely able to wrap my brain around this maybe now. I guess one feature of this pattern is sometimes depending on, so we have these two values, these two names of things, and sometimes we're doing something to one of them. We could either be doing something to one of them and passing the other one kind of straight through, or the other way, vice versa. So then when match one is a function of two arguments, and it's passed in, it's my horrible drawing with a mouse. My goodness. Fish and the empty list. Yeah, get rid of that. As the values, as the first and second arguments from the invocation of when defer to, and then when match one invokes when defer one and just passes in the fish as new lat, but then takes that empty list, which is the second argument that it's given, and conses tuna onto it, and then passes that in as the second argument to when defer. And so you see the pattern. So new lat is now fish, and seen is tuna. When defer one also takes two arguments, invokes last function, conses berries onto new lat. So new lat is berries fish and seen is tuna, I think. And then the last function just gets the length of the first value, which I guess would just, if it's counting the elements, it'd be like 2. So in this procedure, we cons fish onto new lat, and then we cons tuna onto seen. And then he says, we're getting somewhere now. Do you see how at each step we're consing a value either onto seen or new lat? Seen has gotten an instance of tuna, which was the atom we passed to multi-member and co at the start, whereas new lat has gotten the other atom fish. And then berries goes to new lat, and then we'll go to last function. We get the length of berries fish, which is what I said, and we get 2. So that's how multi-member and co works. What does it accomplish? It seems to separate occurrences as the atom A in the list of atoms lat from the other atoms in lat, and then it executes the last function using the list of occurrences in the list of other atoms. In an imperative language like C or Java, you would probably define two variables, one for each list, then loop through the list of atoms, testing each element in the list for equality with A, and then pushing the element onto either of the two lists. Finally, you would call the function with the two lists you built. Consider the differences in this approach. Throughout the loop, you have several variables remaining in scope, which means you have an opportunity to munge one of them accidentally. Also, how modular is this hypothetical code? In C, you could pass a last function as an argument to the procedure that encapsulates a loop, but try it in Java. As TLS points out, the function you supply for use with the two lists is assigned to a parameter named col, because col stands for collector by convention. What is this function collecting? The two lists, of course. But more than that, each use of col, as it changes from when differ to when match, is persisting the values of the list from one step to the next. And that's important because as of page 136, there's been no mention in TLS of an assignment operator. So even if we wanted to define variables while looping through the list, we could not yet. After all, such code would produce what functional programmers refer to with a sniff as side effect. Okay. So I didn't quite follow some of the bigger picture points there, but I think this was helpful with understanding how this works. I'm going to look at some of the other explanations too, though. So there was this graph, or this flowchart. Okay, so this is the initial state, or the initial arguments that are passed in. No lat is false. The equal test is false. So we go to the else clause, and we recursively call. Oh, and the procedure at the beginning is a friend. So then we recursively call multi-remember with these arguments, and he's calling the lambda x1, and the lambda is going to cons carlat, which is strawberries, onto new lat, and then invoke xFriend, or I'm sorry, a friend. So then for this one, this invocation, we're going to get, what are we going to get? Right, the equal carlat a test is true. So then we again recursively invoke multi-remember and co. With the cutter of lat, with tuna as the argument, and with x2, and x2 is going to be a procedure which invokes x1, and cons is, what is it, tuna now onto scene. Is that right? I was looking at the procedure trying to figure it out before I look at the yeah, okay. Trying to build up like an intuition of how this works as opposed to just having to read along. So for the recursive invocation in which the lat is and swordfish, it's not null. It's not, the first value of the lat isn't equal to tuna. So then we go back to the else, and we recursively invoke multi-remember and co with the cutter of lat, and as col we have a procedure which is going to be, I'm assuming it's going to be x3, and it's going to invoke x2 with two arguments. The first is going to be the result of consing and onto new lat, and the second argument will be seen. Or wait, yeah, consing, because new lat is the thing we cons onto when things don't match. So we already cons strawberries. So we're going to be the new list for new lat is going to be and strawberries, and then the scene list is tuna. Yeah, see, we're consing and very exciting. And then swordfish is also going to be const onto new lat. Right, x4 invokes x3 on con swordfish new lat. And then I guess x4 is the procedure that actually gets, because there's no more, because now here lat is null. So, yeah. These flowcharts are pretty good. I wonder what he used to make them. They sort of have an omnigraphal vibe to them. Yeah, I thought that giving the procedures that are generated separate names was very helpful. Like this guy does, and like the flowchart guy does. This explanation was pretty good, but I still was finding it a little difficult to follow with all the nested lambda stuff happening. Okay. That was quite a excursion. All right, so I'm gonna have to rewrite some of this, I presume. It's actually, for this example, it was fine because it was short enough that it didn't run into the thing that gave me trouble. But it was this example where my brain started to feel overwhelmed. So I wrote for this input as a new call. So this is the first, talking about what's going to be the first recursive call. We pass in a procedure. Let's call this procedure Z1. Z1 cons is and onto the first argument taken by the procedure, which is new lat. The result of this consing serves as the first argument to a friend. The second argument taken by the lambda procedure by Z1 scene is passed to a friend directly. I may have done this incorrectly. Well, it's good that I'm saying it out loud. All right, so for and to now, so we go to the else clause. And yeah, we should be consing this stuff onto new lat. Cons and new lat. Okay. All right, so this is the correctly defined Z1 lambda new lat scene. And then so far with this input, like if we then pass Z1 empty lists, it returns true because nothing's been consed onto scene, which is the argument that a friend checks. So with Z2, we cons tuna onto scene, and then you can see the chain of what's happening. If we invoke Z2, before with just Z1, when we const and onto new lat, and then if we gave Z1 two empty lists as arguments, it returned false, or I should say it returned true because it only checks the second argument to see if it's null. But now with Z2, we also were consing something onto the second list, and so, and you can see that Z2 conses tuna onto the second list, provides that to Z1, which conses and onto the first list, and then that all goes back to a friend, which then says, okay, second argument, are you null? And now it's not, so then it returns false. And this shows another benefit of naming these type of arguments that are generated as you go along, is that you can do trace on them, and you can see step by step how they work, which is very useful. Okay. All right, so I'm just looking back at their description of a problem with these, initial values, to see if I think it makes sense now. So this time around, multi-member unco recurs with yet another friend, and they're doing what they call latest friend is my Z1. What is the value of this recursive use of multi-member unco? And they say it's false. But yeah, this is where I felt like I was, like some steps were skipped here. Like, where's Z2? I know they're talking about what the procedure functionally does, but they didn't finish stepping all the way through it, so it's kind of weird. What is the value of multi-remember and quote tuna, ls, col, where? Oh, that's what the length example in one of the things I looked at came from. All right, so we know how it works basically. When the first element of the list is equal to a, it's going to get consed onto the second argument, and otherwise, if the first element of the list is not equal to a, it's going to get const onto the first argument, and so basically, when in the final analysis, the last friend will be getting strawberries and swordfish as the first argument, and tuna as the second argument, and then check the length of strawberries and swordfish, which is 3. Okay. Okay, so the next exercise that they have is, so they remind us of what multi-insert L and multi-insert R look like, and then they want multi-insert LR, and they say hint. Multi-insert LR inserts new to the left of old L and to the right of old R in lat if old L and OR are different. So my solution is pretty straightforward, where basically I check for old L, do an equal test for the first element versus old L. And if that's the case, I just did the same stuff as in multi-insert L, but with the cons old L instead of old. And then the same thing for multi-insert R. I look for if the first element of the lat is equal to old R, and if so, I do similar to what was done in multi-insert R, except for changing the name of the variable. Now, one thing I'm a little unclear on, so then, because I made old L and OR different, but suppose they're the same, and like, is the intended behavior, like if old L and old R are the same, should it do it on both sides? Or does that case not matter? That was an open question I had. I'm just going to leave it like this, but then I'll see what they say. This is a way of combining the two functions. Null lat, carlat, cons new, cons old L, yada yada. Looks exactly the same. Yep. Looking good. The function multi-insert LR and co is to multi-insert LR, but multi-remember is to multi-remember and co is to multi-remember. Does this mean that multi-insert LR and co takes one more argument than multi-insert LR? Yes, and what kind of argument is it? A function? Collector function. Okay. So next thing that they ask, so when multi-insert L and R co is done, it will use col on the new lat, on the number of left insertions and the number of right insertions. Can you write an outline? And yeah, I'm not sure, because how are we keeping track of the number of left and right insertions? Like, I thought we were just making the insertions. I'm just going to see what they did, I think. Or at least I'll peek at what they did and see if I can get the ball rolling. We'll try that first. All right, so new old L, old R lat, col. Okay. Good so far. Oh, I did that thing where I forgot to put cond again. Okay. No lat, yeah. So then they do col 0, 0. Okay, I don't think I would have gotten that. I mean, I guess that makes sense as the if you're gonna be counting something, you want the initial value of the count to be 0. Okay, so you can see they say sure it is just like multi-insert LR, but they're actually leaving the tricky part unfinished in this. So I mean, if that's what we're gonna be doing, because I was actually trying to solve it, like the whole thing. But I guess that's something you think about. Is that in my list, actually? I think it was something Elliot said recently somewhere, maybe on Basecamp, about just like having magic steps. So it's like, well, if I can't solve some part of it, at least, at least have it so that I write out, and then a thing happens, and then figure out as much of the other parts as I can, and then that's something. It's both substantively something because you solve part of it, and also, you can get some satisfaction from actually solving part of it, and then you might see the rest as you go along, as opposed to trying to make it in one big jump. Okay, so this will be like my incomplete version. Yeah. I mean, once I saw the first one that I was incomplete, then it was easy to do that much. And then the base case, which I wouldn't have, was confused about, might not have figured that out on my own. Why is cold used on quote 00, or the empty list 00 when no lat is true? Well, because it says when multi-insert LR is done, it will use call on the new lat, on the number of left insertions and the number of right insertions. So for a lat, we want the base case to be an empty list, and for numbers, we want the base case to be 0. And those are some of the commandments or whatever. The empty lat contains neither old L nor old R, and this means that 0 occurrences of old L and 0 occurrences of old R are found, and that multi-LR will return the empty list when lat is empty. Now it's asking us to analyze that the procedure's not finished yet. Right, this particular one is just the value of the base case for this function because the lat is empty. So we're going to start out in the null condition being true, but we can't evaluate the base case until we know what the function is. Is it true that multi-insert LR and co will use the new collector on 3 arguments and carlat is equal to neither old L nor old R? I mean, isn't it always using the collector on 3 arguments? Like it's a collector of 3 arguments. So the way they wrote the outline, it's always taking 3 arguments. I think the answer is yes. Yes, the first is the lat that multi-insert LR would have produced for CDR lat, old L and old R. The second and third are the number of insertions that occur to the left and right of old L and old R respectively. Is it true that multi-insert L co then uses the function call on cons carlat new lat because it copies the list unless an old L or an old R appears? I feel like they need to break these questions down a bit more. I think the difficulty curve, it's like they realized they were running out of pages or something, so they were just let's stick 3 previous chapters worth of material into the end of this one, like what happened with Babylon 5 season 4. Okay, so this one might actually be this is kind of relating back to, but hang on, because the previous the previous multi-insert LR, I'm sorry, what was it called? Multi-remember and co had 2 lists. If carlat was equal to A, it const carlat onto scene otherwise. So if carlat wasn't equal to A, it const carlat onto new lat. So here we've got 3 lists. Is it true that multi-insert LR and co then uses a function call on, right? So this is a follow-up to this one. So this one is basically in the case where carlat is equal to neither old L or old R, the new collector will be used on 3 arguments. Well, I don't quite understand. Yes, the first is the lat that multi-insert LR would have produced for CDR lat, old L, and old R. That I'm not quite clear on. I understand the second part. Is it true that multi-insert LR and co then uses the function call on cons carlat new lat because it copies the list unless an old L or an old R appears. So that's similar to the reason I was relaying it back. That's similar to what we saw before, where we had unless the A value appeared, we const carlat onto new lat. So I think the answer is yes. Yes, it is true. So we know what the new collector for the last case is. Lambda new lat LR, call const carlat new lat LR. I don't quite understand this fully or like all the purpose of all the parts, but I'm just going to try and follow along and then see if I can get through, and then I'll try and find like another Stack Overflow thread or something so I can get a fuller picture of what's going on here. Where calls second and third arguments just L and R. Yeah, that I don't know. If carlat is neither old L or old R, we do not need to insert any new elements. Oh, I see. So L and R are the correct results for both CDR lat and all of lat. L and R are the correct results for both CDR lat and all of lat. I don't get that either. So what we know so far, and we have even thrown in an extra collector. Oh, it would be something like this. Full cons old R, cons new lat. So we're inserting to the right. We're inserting the new value to the right of the old value. So cons old R, cons new lat, cons new lat, and then you pass an L, you add one to R, and that's it. Col, cons old, R, cons new lat, L, add one R. Yeah, okay. I mean, I was just sort of pattern matching and changing some stuff from the previous one. Like I don't fully understand it, but what is the value of multi-insert LR co new old L old R lat col, where new is salty, old L is fish, old R is chips, and lat is chips and fish or fish and chips. Chips, salty, and salty fish, or salty fish and chips salty. Yeah. Oh, oops. It is the value of. I was just thinking about the value of the lat. Right, but there's two old L insertions and two old R insertions. So you get 2, 2. Yeah, okay. I mean, that makes sense. Is this healthy? Looks like a lot of salt. Perhaps dessert is sweeter. So yeah, it's probably worth analyzing step by step like what's going on with this procedure. So lat is not, so at this first step with these inputs, with these arguments, lat is not null. Carlat is not equal to L, but it is equal to old R, which becomes. The one thing I saw in the Stack Overflows is they recommended that when you're testing this sort of procedure, you use list as the test function because it's like pretty straightforward. Takes a variable number of arguments, just returns what it's given as a list. Because we don't actually have col. If we call Q1 on the what winds up being the arguments that are passed into it, which is the empty list and 0, 0. We see we're off to a good start. We get chips, salty, 0, and 1. For the style of the book, I think they should be doing stuff that's more similar to what I'm doing. I'm breaking it out into steps. But I needed to spend a lot of time reading discussion of this kind of problem, different discussions to really get a handle on this method. Once you've got a handle on it, it's not so bad, but it's a new way of doing things. I think I must have forgotten to add. Yeah, whoops, I actually miswrote the lat input. I'm gonna have to fix some of these. I had this. It's really this. It's not actually that bad. The first 3 steps were the same, so I just have to start changing from the 4th one. Wait. No. Just make sure. Chips and fish or chips and fish or fish and chips. And fish or fish and chips. Fish or fish and chips. Yeah. So you see, there's a lot of steps. I should do this for. Here we go. It's a lot of steps. It's 1 for each word and the lat plus 1 step for the null case. But once you actually break it down, it's pretty simple. Like the other day, I had no idea what was going on with this type of thing, and now it's a little laborious to break it down into each step, but it's pretty straightforward. And I even, like I said, I guessed what this was. I mean, I had a slight misstatement because I was just thinking of the new lat and not what the actual final value would be. But I had some reasonable intuition about what the answer would be produced, what answer would get produced, what values would get returned. Even before I went through this, I still think it's valuable though, because like, you know, my intuition, like 2 days ago was like, so my intuition about these sort of things is not well developed, so it's worth, you know, belaboring it some. Okay. Remember what asterisk functions are? Yes, all asterisk functions work on lists that are either empty, an atom constant to a list, or a list constant to a list. Now write the function evens only, which removes all odd numbers from a list of nested lists. Here is even. Okay, so with reference to remember asterisk, and with a little testing to clean things up as I went along, I think I managed to solve this pretty quickly. So just to step through it really quickly. So we want a function evens only asterisk, which removes all odd numbers from a list of nested lists. And then they give even. I just relied on the built-in even, which I assume is probably the same as the version they have here. I shouldn't say built-in either because I'm loading a file, but you know, the even that was already provided based on what I loaded up. So pretty standard. If the list is null, we'll return the empty list. So if the first element of the list is an atom, I'm going to take that to mean, you know, we're at the level of looking at numbers, at least for the first element, right? So then if that first element is even, we cons it onto a recursive call to evens only with the remainder of the list. If it's not even, we just make that recursive call to evens only with the remainder of the list without consing anything onto it. So we just kind of drop the non-even number. And then if the first element of the list is not an atom, then we cons together the results of calling even only for even only on the first element of the list recursively, which digs down into the list structure vertically, and also the value returned by recursively calling evens only with the remainder of the list, which goes across the list horizontally. And that's it. Now that we have practiced this way of writing functions, even only is, if it's only is just an exercise. Let me paste my so that's my solution. And let's look at their solution. If it's only lambda L con null empty list atom check, even, car L, evens only, coulter L, else, evens only, coulter L, else. Yep, looks pretty solid. Their version agreed. Good times. What is the value of evens only L, where L is, it would just be 1, 2, 8, 10, 6, 2? Yep. Or did I say 1, 2, 8? It should just be 2, 8. 2, 8, 10, empty list 6, 2. Yep. Looks good. What is the sum of the odd numbers in L? 10, 13, 22, 31, 38. Yeah. What is the product of the even numbers in L? Kind of a weird sequence of questions, but okay. 16, 160, 960, 1920. Yep. Oh, I see what they're getting at. Can you write the function evens only in co? It builds a nested list of even arguments by removing the odd ones from its argument and simultaneously multiplies the even numbers and sums up the odd numbers that occur in its argument. Whoa, okay. So we're going to need a evens only, oh, I should give it the right name. Evens only asterisk and co. There's a mouthful. Is going to need to at least take 2 arguments. It's going to need the list, and it's going to need, the list and the collector. And the basic operation is going to be, glad I'm working on this in the earlier part of the evening because I don't know if I'd have the energy for this in the later part. Okay, the mental energy. So it's not that hard, but it's like you have to keep track of a lot of things. So one thing I'm not sure about is, I assume because it's and co they want a collector, but the way they're talking about it, it sounds like maybe they want the procedure to do these operations, like the multiplication and everything, like without it being in the collector. I don't know. Let me just peek ahead and see. Ooh. Okay, so they give a partial outline, I think. Yeah. Well, since that's on the thing you're supposed to read side, I'll read that. Okay, so I see. Let me go more. See, they do have a collector. Oh, so I was on the right path with this, but I need to actually invoke the collector on it. Whoops. Okay. Yeah, let me go more step by step. I mean, I saw a little bit, but an even, or sorry, atom, car L, and then condition, even car L. Yeah, well, I'm not sure, because I noticed that the collector is getting the empty list, the 1 and a 0, which is what I was thinking originally. But then are we not, what are we doing with the original list? I'm a little confused about that. Okay, so we're still passing it to evens only, asterisk and co, coulter L. Then I think we're going to have a lambda. Yeah. Okay, so new list. So then we're just consing first element of the list onto new list. Is that going to retain the structure though? I mean, I guess it's what we're doing. I guess that's what we were doing before. Like consing the first element onto the value returned by evens only. And we multiply first element of the list by p. And then we just pass in the s. Because the multiplication is for the even numbers. If it's not even, we're just going to pass new list n and p, but we are going to sum up the first element with s. I think it's not an atom. Not really sure what to do with the last else. Oh, that's the part they left blank. All right, so I'm consing stuff together, but then they don't actually do that. I was just kind of following the format of the previous iteration of the procedure. I don't understand their answer. It says it visits every number in the car of L and collects the list without odd numbers, product of the even numbers and the sum of the odd numbers. I don't understand. Oh, are they just referring to like, I thought maybe they were referring to this part. Are they just referring to the whole procedure? That's a bit confusing. Like, yeah, if you invoke evens only and co with the car of some list, it's going to visit every number in the car of the list and collect the list without odd numbers, the product of the even numbers, and the sum of the odd numbers. Okay, sure. What does the function evens only and co do after visiting all the numbers in car list? It uses the collector, which we haven't defined yet. What does the collector do? Well, it returns a list of the even numbers, a nested list of the even numbers with the odd numbers removed, the product of the even numbers and the sum of the odd numbers. So they say it uses evens only in code to visit the cdr of L and to collect the list that is like cdr L without the odd numbers, of course, as well as the product of the even numbers and the sum of the odd numbers. So that's pretty much what I said. Does this mean the unknown collector looks roughly like lambda AL APAS evens only in co cdr and then some ellipsis? I mean, yeah, that matches the. Oh, I see that even my screwed up version didn't have. I wasn't doing car and cdr. Yes. When evens only ellipsis is done with its job, what happens then? We return. So it's provided the empty list 1 and 0, and then it calculates those values by invoking the series of procedures that we've built up, like I was doing earlier with where I did multi-insert LR and co, or multi-remember and co, where I had like x1, x2, x3, or q1, q2, q3. It calculates all that. It goes through that chain with the empty list 1 and 0 as the initial arguments. There's a shorter. The yet to be determined collector is used just as before. Okay. What does the collector for evens only? It conses together the results for the lists in the car and cdr and multiplies and adds the respective products and sums, and then passes these values to the old collector. I'm not sure I follow their explanation, but I'm just going to read further. What is the value of evens only in co? List the last friend where L is 91283 yada yada, and the last friend is defined as follows. We never actually presented the finished procedure. I have to find another Stack Overflow thread. Okay. Having difficulty understanding what's going on. Okay, he actually lambda new ps evens only and co. Oops. Evens dash only star and co. I'm sorry. Evens dash only asterisk ampersand co is not a great name for a procedure. Just my opinion. Why is now everything saying there's unbound identifiers in lambda? What's going on? I think I found it. Just had like define with nothing. There's no name at some point in my definitions file, and that was causing weirdness. Okay. So just make sure this works. Did I already define this? Maybe? No. I think this is the problem. I'm consing the first element before I do the recursive call to evens only. I see. Because I was mixing methods. Because I was modeling my answer onto the previous iteration, but we're building up the list in a new place here. We're building up the list of evens in the new list, so we don't need to cons that. Let's see if that works now. Okay, there we go. So that's the output we expect, and now we'll read about why it works and how. Cons sum, cons product, null. So his collector is the same as last friend. All right, so this guy's confused about this procedure, and evens only in co, and he got an answer. I found this section confusing on first reading too, and I only started to get it after I'd read up elsewhere about continuations and continuation passing style, which is what this is. At the risk of explaining something that you already got, one way of looking at it that helped me is to think of the collector or continuation as replacing the normal way for the function to return values. In the normal style of programming, you call a function, receive a value, and do something with it in the caller. For example, the standard recursive length function includes the expression +1 length could or list for the non-empty case. That means that once length could or list returns a value, there's a computation waiting to happen with whatever value it produces, which we could think of as +1 return value. In normal programming, the interpreter keeps track of these pending computations, which tend to stack up, as you see in the first couple chapters of the book. For example, in calculating the length of a list recursively, we have a nest of waiting computations as many levels deep as the list is long. That all makes sense. In continuation passing style, instead of calling a function and using the returned result in the calling function, we tell the function what to do when it passes its value by providing it with a continuation to call. This is similar to what you have to do with callbacks in asynchronous JavaScript programming. For example, instead of writing result equals some function, you write some function, result, ellipses, and all of the code that uses result goes back and goes inside the callback function. Okay, I don't quite understand that, but here's length and continuation passing style just for comparison. We've called the continuation parameter return, which should suggest how it functions here. But remember that it's just a normal scheme variable like any other. Okay, so some of the stuff above was a little unclear, but this is more is looking at the individual sections. The variable names are a little different. So he's looking at this part where we know that the first element of the list is even. Imagine that you have the results of removing numbers, multiplying evens, and adding odd numbers from the cdr of the list. Oh, imagine that you have the results of removing odd numbers, multiplying evens, and adding odd numbers from the cdr of the list, and call them null, product, and sum respectively. So this is a different perspective on this. So there's kind of a leap of faith element in that we're assuming that we were able to figure out the product and the sum and the new list for the cdr, and now we're just adding on, or one element to that. Cons the head of the list onto null. Since it's an even number, it should go in the result. Yeah, that makes sense. Multiply product by the head of the list, since we're calculating the product of evens. And you see I did that, although I'm using that value to do it, but char p for product. Leave sum alone and pass these values to your waiting continuation collector. And when it's an odd number, as before, it passes the same values of null and product to the continuation, along with the sum of sum and the head of the list, right? You see that? Since we're summing up odd numbers. And here's the last one where char is a nested list, which is slightly complicated by the double recursion. Yeah, I was a little confused by the new variables. Okay, so he explains it. So this will be helpful, hopefully. Imagine you have the results from removing, summing, and adding the numbers in char L. Oh, I see. So with the other ones, our leap of faith was about cdr L. But since we're dealing with the nested list, yeah, then we're assuming we have the results from char L. Okay. So that makes sense. Call these null product and sum. Then imagine you have, oh, okay. Oh, I see. So we are doing the car and the cdr, but we have to, it's different. Like the structure of it is different. So imagine you have the results, yada, yada. And same thing to cdr. So the dnull, dp, ds represent the, in the case where we have a nested list, these are the, these represent the list with, from the cdr of the list with the evens removed and the product of the evens and the sum of the odds. Whew. To your waiting continuation, give the values produced by consing null and dnull, since we're producing a list of lists, multiplying together product and dproduct, and adding sum and dsum. This is sort of this is a difficult case for me to follow, but notice each time we make a recursive call, we construct a new continuation for the recursive call, which closes over the current values of the argument L and the return continuation call. Okay, I'm still fuzzy on what happens in the third case where it's a nested list and not an atom. Let's say the input list is nested list 2. Yeah, I'm fuzzy too, so. Which means on the first time through, it hits case 3 with 2 for car and the empty list for cdr. And my evens results for the call, which then goes first down the recurse. Re-entering evens only in call. It is true for the first con null. Yeah, I'm not. So I'm having a little difficulty following that. Oh, this is the flowchart guy. Okay. So I'm going to use this flowchart from the Stack Overflow thread that I found about evens only and co as a sort of map or guide to trying to do something like I did with, what was it, multi-insert LR and co, where I broke things down into individual procedures. I'm going to do it a little differently. As you see, we have these different like tiers of procedures depending on what part of the sublist we're dealing with now. We've got Y, and X, and A, and Z. So I'll just, like, I don't want a million subheadings. No, although, I mean, what does it really hurt? Because there is some value in being like, and now the L is, yeah. So maybe I still will break it up. I don't know. Okay. So performance issues are back, I think, maybe. I don't know why. I thought I'd fix them. Okay. So with the initial state, L is this nested list structure. Col is the last friend. L is not null, right? That's our first test. Car of L is not an atom, so we just go straight to the final condition, or final else, and that's where we're going to start. And you see the structure here, because I want to make sure, I understand the relationship between each part here. So we're saying evens only in co, car L, we've got this lambda, and then cdr L. So this is the cdr L. I'm substituting in real values here because within the procedure, the values will get passed, like within this procedure, the values get passed around, but since I'm breaking it up into pieces in order to see like what's happening, I have to stick in some of the values like more manually. And you see this is the part, this lambda, DL, DP, DS, the variable names or the parameter names are a little different, but this is this part. And the last friend is our col. Typo in my last friend, so I fixed that. Right. Okay. So this is the ultimate value that we get back from evens only and co for the initial values, this initial list here. And what's going on? So from the Stack Overflow, one of the guys explaining this said, imagine for this part of the procedure, as an explanation, he said, imagine that you have the results of removing odd numbers, multiplying evens, and adding odd numbers from the coulter of the list, and call them new L, product, and sum, respectively. Cons the head of the list onto new L. Oh wait, no, this is actually if it's even. This is the one I want. So where CarL is a nested list, imagine you have the results from removing, summing, and adding the numbers in CarL, and you call these new L, product, and sum. Okay, and now that's important. So imagine you have the results from removing, summing, and adding the numbers in CarL. All right. So imagine you have the results from removing, summing, and adding the numbers in CarL1. So I have those numbers. I'm just pulling those from the chart. So like I can see how they're calculated, but the exact process within the procedure that generates those is like not been detailed yet. Like we haven't gotten there. So like imagine you have the results. So I do have them. I don't have to imagine, but I don't know all the details of exactly how those were calculated within the procedure. But so we have those results. Then imagine you have the results from doing the same thing to coulter L. Now we get those results by calling, because it says, and call them dnull, dproduct, and dsum. The names here are a little different. It's dl, dp, ds, but it's the same meaning. To awaiting continuation gives the values produced by con null and dnull, which is this part. Since we're producing a list of lists, that's why we're consing the list together, multiplying together product and dproduct, and adding sum and dsum. And notice in last friend, it conses the sum onto the product onto the new list. So that's why there's this structure at the end. We've got this number and then this much bigger number, and then the structured list. And you can see that the 2.8 is at the beginning there. And then this other stuff appears. But anyway, one thing I wanted to say. So this lambda is returning a procedure of 3 arguments which invokes the last friend and gives it arguments. Where are these arguments coming from? I think this method of going into the procedure actually makes it clear. So this procedure, the DL-DP-DS, is taking arguments from this procedure, evens only and co. And in the specific example that we're looking at, these arguments are the arguments that are being returned when we invoke evens only and co on the coulter of our initial list. So this is the car, and this was the coulter, and so here's the coulter. And then, but then we have another lambda, and above that, and where are these arguments coming from? Well, these are the values generated, and we don't know the exact steps yet, maybe, but by running evens only and co on the car of the list. And so then, and this is the part that I really wanted to understand here, which is part of why I'm going into all this. And then those 2 arguments are put together. They're consed, multiplied, and added and pass to last friend, which then spits out this output. So y1 represents what happens in the final line of only asterisk and co. We invoke y1 with these values, which represent the list of even numbers, product of evens, and sum of odds for this list. The exact mechanism by which we calculated these numbers have not yet been revealed, and we're just taking them as a given for now. I pulled them from the chart. All right, so that should get us started. And when I say not yet been revealed, like it's clear, like you could do the math in your head. It's clear why a human would be able to calculate this. All I mean is we don't necessarily know why the procedure knows this or would have these values yet. So, and just so we're clear, so this number is the result, ultimately, this 2, 8, 16, 10 of calling evens only co on car of the list. Okay. Actually, I messed up. It's y2 is s plus 9. I wouldn't have caught that unless I was trying to very carefully see each step and where each value was coming from. So, one thing to note, so for this procedure, this part of the procedure, one value is coming from the current list, and then the rest of the values are coming from the invocation of evens only and co on the cdr of the list. So we're grabbing the, like right now we have 9, 1, 2, 8. We're grabbing the 9, and we're putting that here, but then the rest is coming from the recursive call, where we're turning a procedure, we're generating a procedure that has a function, and then these 3 arguments, and then we're giving it the values that come from here. So, and that just keeps happening until we run out of list. So 8 is not null. So this is going to be similar to before. I think this is right. Let's see. Yeah, I think I saw this, but yeah. Wow. So this bit from Stack Overflow describes what's happening in the case where you're dealing with an even number. So we see when we get to, and I think I might only do this branch of it because, like, I think I'm starting to get the idea, and I don't know how much value I would get from doing like another dozen of these or whatever. Oh, actually, I should. Yeah, so we do want to do the last step. Okay. So when the list is null, we get we pass the collector, which is I'm calling y5 following this flowchart, the empty list 1 and 0. Y5 cons 8 onto the empty list, multiplies 8 times 1, and leaves the 0 in place, right? So then we have 8, 8, 0. Y4 cons is 2 onto, multiplies the 8 by 2 and leaves a 0 in place. So then we're going to have 2, 8, 16, 0, right? Y3 just adds 1 to the 0. So it's going to be 2, 8, a list 2, 8, 16, and 1. Yeah. Y2 just adds 9 onto the 1, so it's going to be 2, 8, 16, and 10. Let me get a screenshot of that. 2, 8, 16, and 10. And at each step, we know that these values are correct because we're getting the right output at the end. So we've like validated it. And then, and what's y1 do? It's taking these values and combining them with the results of invoking events only and co on the rest of the list and passing them to last friend. And so a similar process is repeated for each other element of each other sublist. Okay, well, I definitely feel like that was helpful for understanding, because I had like no clue what was going on initially. And now I feel like I have some clue. Like, I'm not sure I could build this sort of thing myself, like, but I could at least read along with some understanding now, which is a higher state of achievement than previously. Okay. Good times.